Can anyone confirm whether you can hear my voice or not?
Yes, sir.
Okay. So the topic that I'm going to cover today, actually, some of the topics already covered in physical class. So still, I'm going to repeat the things so that you can have a very good idea on the topics. Okay. So let me share my screen. Okay. I think you can see the screen. Okay. Let's get started. We already covered the topic, the synchronous generator constructions, and also the synchronous generator operating alone with a lamp load. Okay. So, okay. So today we'll be discussing on the synchronous generator equivalent circuit parameters, which are actually formulated using OCC and SCC curve. Okay, that we already discussed. So let's start the topic. The topic is synchronous generator model parameters. And the equivalent circuit of a synchronous generator, which looks like this. Suppose we have the field lines. This is excitation, and here DC supply is provided, VF. Okay, so this is variable resistance RA, and this is the field current. And due to this field, we have the armature voltage, and here we'll have synchronous reactance excess, and we can say armature resistance RA. And the output side, we have the terminal voltage VT. Okay, so if the load is connected, load means electrical load, then there will be current flowing IA. So this current will be flowing if there is a load. If there is no load, IA will be 0. Now, VT can be measured by connecting one multimeter, and we can connect one voltmeter and measure the VT. But it's quite impossible to measure the value of EA. So how can you get the value of XS for a certain generator? Finding RA is quite easy. Just place one multimeter and measure the value of RA. It's quite easy. But finding the value of XS, how can you get that? Okay. So here, in order to get this value, which is named as synchronous reactance. So what we need to do, we need to go for two types of test. One is called open circuit characteristics. Let me write the names. OCC, which is actually open circuit characteristics, and another is SCC, short circuit characteristics. Okay, short circuit. Okay, let me write circuit characteristics. And this particular topic was also covered in your lab course. In your lab, you perform this experiment. How did you do the experiment? If I recall you, first of all, you went for open circuit characteristics. In open circuit characteristics, what you did, you took the generator. Suppose this is the generator. Okay. You took the generator, and what you did, you rotated the shaft by an external force. In our lab, what we did, we used another motor to rotate this shaft. It doesn't matter how you rotate the shaft. The main thing is that if you can rotate the shaft and give a DC supply here, there will be a magnetic field, and that magnetic field will cut the windings here. Eventually, it will produce induced EMF, and finally, it will be acting as generator. Okay, this is the simple way of saying this operating principle. Now, here, if you do not provide any DC supply here, suppose we have a DC supply that is provided here. So if you do not give DC supply here, that means this IF value is 0. This IF value is 0. So if I draw the curve, okay, if I draw the curve, this field current versus this terminal voltage without connecting any load. Okay, if we do not connect any load, let me remove this load to make the things right. Suppose I am not connecting any load. I am rotating the rotor, and I am not providing any IF. So what will be the terminal voltage? This terminal voltage will be exactly equal to EA, because there is no current, so no drop will be here, voltage drop will be here. So VT will be equal to EA. So here, if I take VT under open circuit characteristics condition, which is actually equal to EA, okay, we can say that. Now, if we do not provide any field current, that means there is no magnet here, field current, okay, I am not providing any field current. So what will be the value of EA or VT? There will be some value, okay, a small value. Why? Due to residual magnetism. Due to residual magnetism. So it was supposed to start from 0, but generally in practical case, it starts with a small value, and this is called residual magnetism. And due to the residual magnetism, that magnetic field will cut this wire, and eventually I'll get some induced EMF here. So that will be the value here. Now, if I keep increasing the value of IF, so then EA will also be increased. So this will be increasing linearly. Okay, linearly. After some time, this material will go to a saturated condition. Okay, so if it goes to the saturation condition, then even though I increase IF, there will be saturating conditions, so I'll get the non-linear radial. So there will be saturated. Okay, so this is IF versus VT, or IF versus EA. EA and VT, and they are equal under open circuit condition. So we are getting this curve. Okay. Next, in our lab, what we did the same operation, making this side shorted. So if I short this, let me draw this. So I'm shorting it. Okay. So shorting something is a very dangerous thing. Okay. So you need to be very cautious before performing this experiment. Now, for a small amount of EA, there will be huge current through this line as this side is shorted, and we know this XS value and RA value, they are very small. This is nothing but a short-circuited coil. Okay, so RA will be very, very small with respect to XS, and overall XS is also small. So overall the Z value is quite small. So we need to be very cautious about that. So what we are going to do, we are going to perform the same experiment like this. We'll take the same curve. Okay, that is also IF versus this IA. Okay, now previously, why didn't I take IA? Because at open circuit, IA will be 0. Here, why am I taking IA? Because Under short circuit condition, with this terminal voltage will be 0. As these two parts are shorted, so this terminal voltage will be 0 because both the sides are shorted. Now we are going to take the value IA versus IF. Now for a small amount of IF, IA will be increased drastically because this side is shorted. So what is the maximum current that I can take? When we'll perform this operation, we'll connect one ammeter here, ammeter. Okay, I know my generator take a maximum amount of current, which is for which this generator is designed for, and that current is named as rated current. That current is named as rated current. So for IF equal to 0, current will be very low, but for small, if I increase IF, current will be increasing like this way. Okay, practically we'll get a straight line, and for certain value of IF, we'll get the IF rated. So stop there, because if you increase IF and if the generator starts providing more than the rated current, it may cause the damage of generators. Okay, so we'll stop here. And for this IA current, you will not be able to see the saturated condition, because before we reach to the saturated condition, our IA will reach to the rated current condition. That's why it's quite impossible to see the saturated condition here. Okay. Now under short circuit condition, what is the value of excess or RA? So we can say RA square plus excess square whole root. That will give us what? Actually EA over I. Now for any particular value of IF, we need to find the value of EA and we need to find the value of IA. Now suppose when for any particular value of IF, if I take the value for any particular value of IF, for example, this value. Walaikum Assalam. Any question?
Please, sir, could you explain again why we cannot go up to the saturated current?
Saturated current, because if we keep increasing IF, IA will be increased. Okay. So IA will be increasing. What is the maximum? Because current may damage your windings if the current goes to beyond a certain value. Okay. So whenever current will reach the rated current, will stop increasing IF. Okay, we'll stop increasing IF. So that rated current is much more less than the saturated current. That's why you will not be able to see that saturated condition. If you want to see that, your windings will be burnt. That is the problem. Okay, that's why you won't be able to go up to saturated condition. Have you got it? Well, so
But sir, theoretically, IA should be infinite, right?
no, theoretically IA should not be infinite, because we already have these two values, XS and RA. They are small, but they have a value. Theoretically they have a value, right?
Yes, sir.
Okay, let me explain this thing in different note. So suppose I have a wire. Okay, let's take the example is in DC. Okay, I am providing DC supply. Okay, now this wire can take maximum 10 ampere. This is the rated current for this wire. What is the value? 10 ampere. Okay, now I am saying that this resistance has a very low value. Okay, for example, this resistance is 0.1 ohm. Okay, now if I give 0.1 voltage, what will be the current?
1 ampere.
1 ampere. Very good. So 1 ampere falls under the rated current, right? So it's below rated current. So 1 ampere current is fine. But when I'm getting 1 ampere for 0.1 voltage, okay. But if I give a normal voltage, for example, I'm 10 voltage is not that much, but I'm giving 10 voltage here. So what will be the current? Current will be what?
100.
100 ampere. 100 ampere much more higher than the 10 ampere.
100.
Why? Yes. Why I am getting 100 ampere? Because of this small amount of value. But this small amount of value, still, it will take less than the rated current for small amount of source voltage. Have you got it? So what I am saying that even you are saying that as this side is shorted, okay, so theoretically I am supposed to get infinite amount of current, but definitely will get very high amount of current. But which value of EA for this 10 volt, or for a normal voltage of EA, I'll get very high amount of current, but there will be some resistance here in the windings. Okay, so that's why for small amount of voltage, I'll not get IA that much. But for if I increase IF a bit more, then after some time it will reach up to rated current. Okay, when it reaches rated current, then we will stop. Is this clear?
Sir, if we don't stop the IF, the wire will be burnt out
If you
and
keep
there will be no current.
No. When this wire is burnt out and they are disconnected, there will be no current. So my motor is damaged. So there is no point of discussing further, right?
Yes, sir, I understand.
Okay. So now we have got these two curves. Okay. Now our RA square plus XC square equal to EA over IA. Now from this curve, for any value of IF, I'm trying to figure out the value of IA. So for this value of IF, what is the value of IA? I can find it from here. So that can be figured out from SCC curve. Okay. Now at this point of same IF, okay, whenever I'm providing the same value of IF, that will produce same EA. Okay. So what is the value of EA for that IF? That we already figured out from the OCC test. So take the same value here, okay, and take the value of EA from here. So you put the same value from the OCC curve for a particular value of IF. Constant, should I say constant value, or same value? I should say same value of IF. Okay. Okay. I equal to same value for
Sir,
both cases.
corresponding value এটা
Corresponding value means you can take any value. Suppose if someone says that I want to figure out the value of this RA square plus XS square for, suppose IF equal to 0 here, 1 here, 2 here, 3 here. This is example. Someone is taking 0, 1, 2, 3. Okay. For 3, someone is taking. Now you can say, sir,
Yeah.
I'll take for 2. So take
So
2.
for corresponding 3, we get in the IA versus IF curve, we get, let's say it is 3.2 for EA versus IF curve
Yes.
in the x-axis. So is
Right.
okay. Thank you, sir.
And for 2, if someone takes this 2, okay, if you take this ratio, as both these are linear, you'll get the constant value, same axis value. Okay. So if I show you the curve from the book, then things will be more clear. Okay. Let me show you the figure from the book. This is the figure from your Chapman's book. Okay. What they did, IF versus EA. This is the OCC curve. Okay. IF versus EA. This is the OCC curve. This is the VT curve, VT axis, and they are plotting the same or two figures in the same graph. That's why it looks like this. And this is the second y-axis. Second y-axis, IF versus IA. So that is this. Okay. You see, we have two regions. One is saturated region from here to here and unsaturated. In saturated region, wherever you take the ratio, you are getting the constant value excess. That's why this is straight line. And in the saturated region, okay, there you are getting something like this curve, a curve. Okay, let me show you the figure here again. Then things will be more clear. Okay, suppose there are two parts. Okay, from here to here, this is linear. So if you measure the value of excess from here to here, by taking any value, you will get excess constant. Excess equal to constant. Okay, for which region? From here to here, this region is named as
Linear.
unsaturated.
Okay.
Linear, or you can say linear as well. Unsaturated. And from here to here, this region is called saturated. Okay. So in excess will be constant for unsaturated region. Okay. And excess will have a very value for saturated region. So excess that is measured in the unsaturated region, that is named as unsaturated synchronous reactance. Okay, I repeat, excess that is measured in the linear region, that is named as unsaturated synchronous reactance. Let me write it here for you. Excess measured in the linear region can be said as unsaturated synchronous reactance. Okay, this is one term, and I can say another term, excess measured in the non-linear region is named as saturated synchronous reactance. Okay, clear?
Sir,
So
sir,
bolo.
স্যার যে বইয়ের গ্রাফ
শুনতে পাচ্ছি।
পার্টটা একটু আরেকবার দেখাবেন।
Sure. Let's see the graph part from the book. Okay, tell me.
স্যার এইখানে এক্সএস এর এই যে গ্রাফটা এরকম কেন হইতেছে?
Okay, let's go back to our lecture part. In unsaturated condition, in linear region, what is the value of excess? Excess will remain constant, right?
Yes, sir.
Right? Though I change IF,
Yes.
excess will remain constant. Okay. So if you go back to the book condition, from here to here, I'm having the linear region. From here we are starting the non-linear region. Okay. So if from here to here excess is constant, so definitely that will be straight line. Irrespective of IF, I'm having the constant value, right?
Yes, sir.
Suppose it
মানে
is
স্যার
6.
এখানে এক্সএস এর ভ্যালু বাড়তে পারতো না? মানে আমরা যখন স্যাচুরেটেড যেতেছি তখন কি এক্সএস এর ভ্যালু আরো উপরে যেতে পারতো না?
No. For two linear line, if you take the ratio of two linear line, that is always constant, right? Do you know the ratio of two
Yes,
straight
sir.
line is
আমি
constant?
আমি স্যার আমি বলছিলাম যে স্যাচুরেটেড রিজিয়নের জন্য এক্সেসের ভ্যালুটা এইটা কি বাড়তে পারতো আরো
No, it
কনস্ট্যান্ট
will be
রেশিও থেকে?
reducing. Why? Okay, no, it will be reducing. Why? Tell me. Because our equation says my excess equal to EA over IA. Okay. Now, after a certain value, EA is being saturated, not IA. EA is being saturated. Okay. So if EA is saturating, IA is suppose increasing. So combinedly excess will be reducing. That is what our math says. Here you see my for any value of IF, how can I get excess? This divided by this. Now here the upper part is being reduced and lower part is increasing with a certain constant value or certain slope. So definitely excess will be reducing, right?
Yes, sir.
Have you got my point? What I am saying?
Yes, yes, sir.
Okay. So this is from your book. Okay, as we are here, let me review the topic from your book as well. This is chapter 5, from where I am covering synchronous generators. And I already discussed about synchronous generator construction in our previous physical classes. You can go through the book topics, okay? Things will be more clear for you. This is the speed of the rotation for of a synchronous generator, as we told that in order to get 50 hertz, what should be the speed? We can figure this out. Okay. And here it is said that even though I increase IF, after some time, phi will be phi will not be linearly increased, rather there will be a saturation. That's why you get saturated value of EA. Okay. So this is the equation for generating voltage, and this is the equivalent circuit formulation. Okay. Eventually find, this is for 3-phase system, and per phase equivalent circuit, we got it like this. I drew this or I showed this in your physical classes. Okay. Later on, we found out the phasor diagram for different types of load. One is, this is for inductive load. We already plotted. This is for capacitive load. Current is leading. And another we have for resistive load that was shown earlier. Okay. And if we increase different types of load, what happens? This is already covered. If we increase different types of load, this is the curve for finding the value of synchronous reactance. Okay. So if we increase different types of load, you can see this is single generator connected with a load. And I told you one of the applications that our IoT generator, when it operates alone with IoT campus load, then we can correlate this condition with our IoT case, or our IoT case can be correlated with this condition. Okay, a single generator supplying a single load. Okay, so a single generator is supplying a lumped load. So this is under this circumstance, what we saw that if I increase, previously this was the load, if I increase inductive load, our terminal voltage decreases. Okay, decreases significantly. If I increase resistive load, our terminal voltage decreases, but there is a slight decrement. And if I increase capacitive load, our terminal voltage increases. That is written here. I showed you these things in your class, that if lagging loads are increased, terminal voltage decrease significantly. Okay. And if unity power factor loads are increased or added, there is a slight decrease in terminal voltage. And leading power factor, leading loads are added, terminal voltage will rise. Okay. So these three conditions you need to remember. And there is a term called voltage regulation, V no load minus V full load divided by V full load. So that we already discussed. Okay. So let's go back to our lecture. Any question up to this much? No? So I think you can figure, now you understand how we can uh, get the value of this excess. Okay, there is a comment in the comment section or chat section that someone is asking something. Let me see. Sir, is there any actual capacitive load? Well, generally we don't have capacitive load. We do not have capacitive load as load generally. That's why in order to mitigate most of the reactive powers consumed by inductive load, we use extra capacitive or extra capacitive load connected in parallel with those inductive loads. Okay, in order to improve our power factor. Okay, that all of you know, I think, from your previous AC circuit knowledge. Okay.
Sir,
Hmm.
hello. Sir, in the
Yes, I
reactance
can hear you.
diagram, the reactance is a declining, exponential curve. It's like it's declining in exponential way. But if you see the expression, xs square, Ra can be negligible, so xs square, right? So root over xs square means xs. So if the
Yes.
EA by IA is decreasing in a linear way, so xs should be a linearly declining curve.
Yes, yes. If they would be declining in a linear way, both of them, then
Yeah.
what you are saying, that is true. But the problem is they are not declining in a linear way. In the saturated region, things will be not like that. Okay. Both of
Okay,
them
sir.
will not be declining linearly, as we saw from our books card. Okay.
Okay, sir. Okay, sir.
But what you said, if they would be declining in a linear way, both of them, then we would get a declining excess, which would have a linear in nature. Okay. So that is the case. Okay. Now, next we are going to start another thing that is already described in our in our physical lecture, but still I am describing it here for your better understanding. Okay, that is, suppose we have a generator. Okay, now from our previous vector diagram, we saw that if I increase inductive load, okay, if I increase inductive load, that means Q load, reactive power, okay, Q load, what happens to the terminal voltage? Can anyone tell? What happens to the terminal voltage? Terminal voltage decreases, right? So, do you remember this phenomenon from the previous lectures? The vector diagram, and I showed you three different lines or sentences from Chapman's book that if I increase lagging load, terminal voltage decreases significantly. Okay, so lagging load actually causes the decrement of terminal voltage significantly. Are you getting me? So if there is no load, suppose I'm getting this amount of terminal voltage, but if I increase the Q load, the terminal voltage will be decreased, something like this. So there will be a slanted line having a constant slope. And under this circumstance, suppose this is 220 voltage, for example. Now, if I connect a certain amount of Q load, suppose this amount of Q load, so what will be the terminal voltage? Terminal voltage will be reduced to, for example, 180 voltage. So this is not desired. We are buying one single generator. For example, we are buying a generator here and running the generator from an external source. Okay. Now I'm connect with, if I do not connect and measure the voltage, I'm getting 220 voltage, fine. But whenever I'm connecting a load, this amount of Q load, Okay. The terminal voltage goes to 180 voltage, but I need to maintain 220 voltage all the time. What to do? Any idea? I already discussed in the class. What to do? We need
Have to
to
add capacity.
increase
Excitation.
uh, increase excitation. Very good. We need to increase excitation. Suppose from here I'm getting 180 voltage, so I need to increase excitation in a way so that this point comes here,
No fuel.
220 voltage. Okay. So whenever this point will come here, with this excitation, with this amount of load, well, I'm getting 220 voltage. I'm getting 220 voltage. Okay. But under that excitation, if I remove all the load, then terminal voltage will be increased. It will go, for example, 240 voltage. Again, in order to maintain 220 voltage, I need to decrease excitation. So whenever I'm connecting load, I need to increase excitation. Whenever I'm disconnecting load, I need to decrease excitation to maintain 220 voltage constant voltage. Clear? So this is what we need to maintain. Okay. Again, this is for Q load. Again, for real load, P load. Okay. If we, as we discussed in the class, all these topics are discussed in the class. I am just rediscussing here for your clear understanding. If I connect any P load, real load, okay, real load will affect the frequency. Why? If there is a real load and connected with the generator, there will be current flowing through this, and this current will produce an RMF, which will try to oppose the rotation of this rotor. So if I do not increase the diesel supply or the force in the shaft, if I do not increase that supply, and this rotor is getting opposing force, so eventually this rotor speed will be decreased. If the rotor speed is decreased and it is less than synchronous speed, so supply frequency will also be decreased. So if I increase any type of load, eventually supply frequency will be decreased and this will have a curve like this. Okay. So this is the case. So suppose you buy a generator without connecting any load, it was giving 50 hertz supply. Okay. Now, whenever you are connecting a load, real load, due to this connection, the supply frequency goes to 45 hertz, which is not desired. I need to maintain 50 hertz. In order to maintain 50 hertz, what I need to do?
রোটেশন বাড়াই দিতে হবে শ্যাফটের।
Yes, we need to increase the rotational speed. Okay, how can we do that? Suppose this
By
is diesel
giving more
engine,
diesel.
so we need to provide more diesel. Suppose this is steam engine, we need to provide more steam. So under this condition, the rotational speed should be increased. Okay, so this will come here. Okay, once I increase the speed under this condition, so this will be the new curve. Okay, this should be parallel. This is the new curve. Now, under this condition, if I remove this load, then this point will come here, which is higher than the 50 hertz frequency. When it comes here without any load, again, you need to reduce the rotational speed so that it maintains 50 hertz. So all the time you need to control this speed. Two things you need to control. One is the excitation and another is rotational speed of the rotor. All the time you need to control. Okay. So from here, I'll continue in the next physical class, but I wanted to take this part in addition to your physical classes. I wanted to take this part online so that we can have very clear understanding. Now, do you have any question up to this much?
Assalamualaikum, sir.
Walaikum salam. Yes.
Please, sir, I wish to ask if the class was recorded. Actually, I had some network issues, so I couldn't get it clearly. The whole class.
So you wanted the recording of this class?
Yes, I had some network issues, so I couldn't get everything.
Okay, no problem. So I gave permission to ample number of students to record my sessions. I want one of my students to share these recordings with your fellow mates. Okay, so who will do that? Anyone? I don't know whom I gave permission, but there are a good number of students who are recording. Okay, roll number 102. He is recording. Or one of the seers. 201 is seer, right? Our seer.
Yes, sir. Yes, sir.
Okay. Can you share your recordings to your
Yes,
fellow
sir.
classmates?
Yes, sir. Yes, sir. I will. I will share.
Okay. Share this in your internal group. Okay. Do not disclose it with others. Okay. Any other questions? No question. So if you do not have any question, I'm keeping up to this much. Inshallah, we'll be meeting in our next physical classes. Okay. Thank you for joining the session.
Okay. Assalamu alaikum.
Wa alaikum salam.